All the progress you make in the game has to be saved so you can come back later and continue where you left off. That means every machine you placed, every piece of loot you got from monsters, the durability left on your tools, and your whole inventory have to be preserved. In Godot, in order to save a piece of data to disk, it usually has to be represented as a resource. Resources are Godot's way of packaging data so the engine knows how to save it to disk and load it back later. In order to do that, I created several scripts, each of which extends the resource class. I also give each one a class name so I can easily reference them from other scripts. Next, I define the fields that I would like to save to disk. In this example, it's the position of the machine and its current energy. I also have an init function that lets me create a new instance and fill in the values when I'm preparing to save. Inside each machine, I have a serialized function which is used to create that resource for saving purposes. Here is another example of a resource, in this case a chest. Note that inventory slots is a custom class that stores items and is also a resource. This means that you can nest your resources inside other resources as much as you want. You can also serialize collections like arrays and dictionaries. Now let's look at how resources are aggregated into a larger resource to contain the information about all the items in the world. In this example, I am saving all the information about the dimension that is being serialized. The information about the machines is preserved, as well as the dimension's type and its seed, which is used to determine whether it's a dungeon or the surface, and how everything is laid out in the world. I'm also preserving the time of day, the items that are lying on the ground, the size of the dimension, and the player's spawn point. The player is saved as a separate resource from the world, since the player can travel between various dungeon levels and the surface. The code for the player resource looks like this. This stores the player's position, his inventory, which dimension he is currently in, the item currently held in the cursor, and his health. These two bundles are almost ready to be saved to disk. But before we do that, we need to determine where to save the files. Godot exposes a special path prefix called user, which points to some directory based on your operating system. This is the folder where you can store persistent data files. This is how we get the paths for the main save file directory, which includes the player resource and any dimension that might be generated within this single world. To get the full path, though, we need to construct it. Every world in industrial dungeons is uniquely identified by its seed, so we can use that in order to create a separate folder for it. Another function that Godot exposes is path join, which is used to chain folders into a path. The constructed path might look something like this for the surface dimension within a world, like this for a dungeon dimension, and like this for the player resource. The user prefix could resolve to something like this, depending on your system. As you can see, every world gets its own folder named after its seed, and inside it you have either player.res or a file named after the dimension seed. Once we have the path and the state of the world, which is the resource with all its data filled in, we can call a special function to save it. That function is called save and lives in the ResourceSaver class that is provided by the engine. The call to save saves a resource to disk at the given path and returns an error if there is any. You might have noticed that I passed a third parameter to this function, which is flag compress. This flag makes the whole file smaller, around 5 to 10 times smaller in my testing, from 250 kilobytes down to 38 kilobytes. One thing to watch out for is that ResourceSaver.save will not create the folder structure for you. In that case, you will have to use one of these two functions that will create them. Another thing that gets saved is the settings, which you saw in the previous video. Now let's look at how that actually works. Each control in the settings view is listening to the toggled signal. This signal calls a method that does two things. It updates the world to reflect that change and also saves the updated config file. One nice thing about using the ConfigFile class is that we don't have to create additional resources since config is a simple mapping from keys to values in a given section. The reason I am loading the config file first is so that I can update it rather than overwrite it. On the other side of saving is loading. The first steps are similar. I still need to figure out the correct path using the WorldState. But instead of calling save, I now call load. Loading means deserializing each resource, basically taking the raw data and reconstructing all the machines, their positions, inventories, energy, and so on, exactly as they were when you left the world. The list of loadable worlds was presented in the previous video, so I'll only show it briefly. The load function can fail to load the world. In that case, the message will be displayed at the bottom to inform the user what went wrong. A file might get corrupted, it might fail to migrate, the file might have been edited in an unexpected way, or it may fail for some other reason. One important aspect of save files is how they evolve when the game gets updated. What would happen if I tried to add extra fields or remove some of them from a resource? Well, the engine expects the resource to have a specific format that was defined when the resource was being serialized. If the engine tried to deserialize a resource, but ended up loading a different structure, then it would throw an error related to deserialization. To fix that, I came up with the idea to create multiple versions of a resource. To go from one version to another, a resource has to be migrated, meaning that its data has to be transferred to the newer resource. For example, this is what version 3 of the player resource used to look like, along with its migrate function to version 4. In this case, I've added the health field and provided a migrate function that returns the new player resource with the default value for health of 50. Now, every time a resource is loaded at a given path, its version has to be checked. And if it is outdated, it will call the migrate function until the latest version is achieved. This ensures that the player resource is always up to date by going through the entire history of updates that need to be applied step by step. The same thing is done for dimensions. You might be wondering, when is the game saved? Well, saving is triggered in any of these 4 cases. Number 1, it gets saved when the game is closed. This listens to the notification callback that the engine provides. This notification is received from the operating system when a close request is sent. For example, the close button on the window, Alt plus F4, etc. This ensures that the game is saved before the application gets closed. Number 2, it gets saved every 5 minutes. The game runs a clock that keeps track of autosave. Number 3, it gets saved when you switch dimensions. So when you either exit a dungeon or enter one. And number 4, it gets saved when you press either main menu or exit in the escape menu. So that's how saving and loading work in the game. Your progress is stored properly, it stays compatible when the game gets updated, and your settings are remembered. In the next video, we might look at liquids, tanks, pumps, oil drills, and the piping between them. Thanks for watching!